Good day, everyone. My name is Shankar, and I'm doing my PhD in the Department of Mathematics at RWTH Aachen in Germany. And today I'm going to be discussing about a higher order adaptive method for computing the exit times of stochastic processes. So I would like to give a quick introduction regarding what exit times are and the problems associated with it before I head over into the algorithm that I want to discuss. So what is the exit time? Exit time is the first time that a process actually crosses a threshold. And this is very important when it comes to finance and in physics. So for example, in finance, a person might be interested to know uh, which is the optimal time to buy or sell a stock or an option so that he or she can maximize the profits associated with the stocks or the options. So exit times plays an important role in finance and in physics. A physicist might be interested in computing uh, the minimum time required in order for a particle to cross a potential barrier, and yeah, so on and so forth. So exit times play a very important role, and exit times relate to the Feynman-Katz PDE, which we'll see later on as we go along in the discussion. The major issue with using the PDE to compute the solution to the mean exit time of the stochastic process is that as the dimension of the problem increases, the computational complexity also increases. So it's not easy to compute the solution to the PDE. So what is the alternative option that we have? So the alternative would be to use Monte Carlo techniques or multi-level Monte Carlo techniques in order to compute the mean exit time. And for that, we would have to sample the trajectories of the STE, considering that it's not always possible to obtain the exact solution to an STE. So you would use numerical schemes like Euler, Maruyama, or Milstein schemes in order to sample the trajectories. But the problem with sampling the trajectories at discrete time points is that we run the risk of missing the exit of the stochastic process through the boundary in between the time steps. So this means we would be estimating a completely different time when the process exits through the boundary when it could have already exited before. So our methodology aims at minimizing this probability of missing the exit by refining the time step size as the stochastic process gets closer to the boundary. So we assume that the boundary of the domain is smooth, and we consider that the drift and diffusion coefficients are regular enough. So these are the assumptions that we make. On top of that, we also assume that the diffusion coefficient is uniformly elliptic, which we would need again for the rates that we want to compute. So with this, we define the mean exit time as given in equation 3, as can be seen in the slide that's been shared. From this, we can also see that the mean exit times are also Lipschitz continuous. That is again an assumption that we make. This especially holds true for like very simple cases like Wiener processes and for processes that are regular enough. So with this, we move on to finding the optimal region where we start refining the time step size. So we do that by first partitioning the domain D into a critical region and a non-critical region. So what we basically do is we refine the time step size when the process is inside the critical region. And when it's outside the critical region, we don't refine the time step size. We just use the time step size that we started with. So as can be seen from equation 9, if the numerical stochastic process lies inside the critical region, we use a time step size of delta t squared. Or if it lies outside of the critical region, we just use time step size of delta t, where delta t is fixed time step size. So the way we choose the critical region is based on the fact that the running maximum of the stochastic process does not exceed more than delta. So the maximum step that the process can take is bound to be less than delta. So that is the criteria that we are aiming for. So this ensures that the process, no matter where it starts from, it enters into the critical region before it exits. So this is the idea behind our algorithm. So on bounding this probability, we see that we are able to achieve a strong error rate of order delta t. And with regards to the computational complexity, we see that the expected cost involved in performing this adaptive or implementing this adaptive algorithm is of order delta t to the power minus 1 times log delta t to the power minus 1. So in the numerical results section, you can see the problem parameters that we used in order to perform the numerical tests. So we consider a very simple case of a one-sided boundary where we use the geometric Brownian motion given by equation 16, and all the parameters that are associated with computing the mean exit time for that are given in the table as stated. And it can be seen from figure 2 that we do obtain a strong error of order delta t for the mean exit times, and the computational complexity is of order delta t to the power minus 1 log delta t. So yeah, so this basically corroborates with the theory that we are developing currently. And I would like to conclude by saying that this not only improves the weak error, as was suggested by many other papers that are referred to below, we can also see that it improves the strong error. So this method, having improved the strong error, can be implemented with other techniques like multi-level Monte Carlo in order to achieve better rates. So that is what we are aiming for. And the good part about this methodology is that it can be extended to multiple critical regions. So you could practically perform time step size refinement more and more as you get closer and closer to the boundary. So thereby you can improve the convergence rates without increasing the computational complexity. So this basically comes from the fact that on carrying out the test that we had, we saw that the overall computational complexity was still at the same order as one shown here, even when we use delta t cubed. The only thing that has to be taken care is the critical region width that we choose for using time step size delta t cubed. But we could end up with an order of delta t to the power 3/2 for the error rates, while still maintaining the same computational complexity. So that is the second point that's been mentioned. And you can also extend the methodology that we have right now to higher dimensionalities. So this makes the scheme very versatile, and all you have to basically keep track of is the distance function of the process to the boundary. So yeah, if you have any queries, can refer to the references down below, and I'll be happy to answer more questions during the poster presentation. Yeah. Thank you for having me in KAUST, for letting me present this work, and see you all soon. Thank you.